Today on AI Paper Podcasts, we are covering DFlash, block diffusion for flash speculative decoding. This one's from Jian, Chen, Yesheng, Liang, and Zhijian from UCSD and ZLab.
Right.
And if you work in LLM inference, you know the core problem. These models are slow. It's the autoregressive bottleneck decoding one token at a time.
Always, one by one.
So, speculative decoding has been the industry's fix. You use a small draft model to guess ahead, but there's a huge flaw in even the best methods, like EGLE3.
There's still autoregressive, the drafter is.
Exactly. So your drafting cost just grows. You want to draft 10 tokens, you pay for 10 forward passes.
It scales linearly, and that just kills your speed up.
This is where DFlash comes in. It introduces a lightweight block diffusion model for drafting.
Which is a totally different approach.
It generates draft tokens in parallel, a single forward pass. And it does this by conditioning on context features it pulls straight from the target model.
And the results are, they're pretty staggering.
Over 6x lossless acceleration on models like Qwen 3.8b, and it's up to 2.5 times faster than EGLE3.
The takeaway here is really that diffusion models might have found their killer app, not as the main model, but as this hyper-fast drafter.
That is a very efficient summary.
And I think the key metric that really jumps out from this paper is that lossless part.
Well,
we aren't approximating.
No.
We're getting the exact same output distribution, just 6 times faster. A purely architectural speed up.
Exactly. So let's back up a bit and, set the stage. We're talking about the bottleneck of LLM inference.
Mm-hmm.
If you've used any of the new reasoning models, like, say, OpenAI's O1 or DeepSeek R1, you know the pain. You type a prompt, and then you wait.
You wait a long time. Right, because those models are generating these huge chains of thought. We're talking thousands of intermediate tokens before you even see the final answer.
And that hits what we call the memory wall.
Yeah, the memory wall. It's a huge deal in GPU computing.
I feel like we hear this term all the time, but let's actually unpack it for the engineers listening. Why is generating text specifically hitting this wall so hard?
So LLM inference is fundamentally memory bound. It is not compute bound.
Okay.
Think of your H100 GPU. It has these massive compute cores, tensor cores, that can crunch numbers incredibly fast. But they're just sitting there, idle, most of the time.
Why? What are they waiting for?
They're waiting for data. They're waiting for data to be fetched from the high bandwidth memory, the HBM. It's the data transfer that's the bottleneck.
So it's the data transfer speed that kills you.
Precisely. When you generate tokens autoregressively, one by one, you have to load the entire model's weights from memory to the compute units for every single token.
For every word.
For every single word. You load 70 billion parameters, you do a tiny bit of math to get one token, and then you dump it. And then you do it all over again.
It's like driving a Ferrari in stop-and-go traffic.
That is a perfect analogy.
Yeah.
You have all this horsepower, but you can't use it because you have to stop at every single intersection.
And this is why speculative decoding was invented, right? To try and clear up some of that traffic.
Exactly.
Okay, so for listeners who might just be tuning into this whole optimization space, can you give us the quick technical definition?
Sure. Speculative decoding is like having a fast intern and a slow professor.
Okay.
The intern, that's your draft model, quickly scribbles down a guess of the next few sentences. Then the professor, the big target model, reads that draft all at once in parallel.
And if the intern was right?
The professor signs off, and you've saved a ton of time because you verified a whole block in one go. If the intern was wrong, the professor just corrects it from the first mistake.
But this is where DFlash sort of picks a fight with the current leaders. The paper argues that even our interns are just too slow.
Precisely. You take EGLE3, which is, arguably the state of the art right now. It uses a small transformer layer as the drafter, but it's still autoregressive.
So one by one?
Still one by one. If you want that intern to guess 16 words ahead, the intern has to write word 1 and feed that back to write word 2, and so on, sequentially.
So the cost of drafting just scales linearly.
Exactly. Your cost is n times the time per step. And eventually, if you try to draft too far ahead, the time you spend drafting just eats up all the time you saved. You hit a ceiling.
Which is usually what, like 2x, 3x speed up?
Yeah, you're lucky to get that. You just can't push it further because the draft model becomes its own bottleneck.
And this is where DFlash flips the script. They ask, why are we drafting sequentially? And they bring in the diffusion element.
Right. And historically, diffusion models for text have been, well, let's say a mixed bag.
That's putting it politely.
Yeah. Diffusion works wonders for images, generating pixels in parallel from noise.
Yeah.
But for text, for discrete tokens, it's harder. Diffusion LLMs or DLLMs rely on iterative denoising.
And to get high quality, you need a lot of steps.
A lot of steps. If you need 50 steps to generate a sentence, you're actually slower than the autoregressive model you were trying to replace in the first place.
So it's a trade-off. Autoregressive is high quality but slow. Diffusion is fast, parallel, but historically lower quality or just inefficient.
And DFlash says, let's hybridize. Let's not pick one. Use the diffusion model for what it's great at, speed and parallelism, but only for the drafting phase.
And then let the big autoregressive model handle verification.
Exactly. So you ensure the quality remains perfect, absolutely lossless.
It's the best of both worlds approach. But the math on the latency is what's really cool here. Because it's block diffusion, the drafting cost is basically constant.
Ideally, yes. In block diffusion, you predict a whole block, say 16 tokens in a single forward pass. So whether you're predicting 4 tokens or 16, the latency is virtually the same.
So it's O of 1 relative to the block size?
Versus O of n for autoregressive.
Yeah, that just opens up a huge design space. If the speed doesn't get worse, you can afford to make the draft model smarter.
That's the key insight. You can make the draft model deeper, add more layers to boost its accuracy, without paying that heavy latency penalty you would in an autoregressive setup. You're decoupling the smartness of the drafter from its speed.
Okay, let's get into the architecture, the nuts and bolts. How do they actually build this? Because you can't just slap a diffusion model next to Llama and, hope for the best.
No, you can't. The paper mentions this core concept. The target knows best.
The target knows best. What does that mean?
It's a really fascinating insight, and it references some other recent work. The idea is that the large target model, a big 70B parameter beast, it already has information about the future tokens encoded in its hidden states.
It's like the model subconsciously knows what it's going to say next before it actually says it.
In a way, yeah. The hidden representations in the deeper layers capture these long-range dependencies and sort of the trajectory of the text. DFlash exploits this.
So it's not asking the small model to just guess from scratch.
No, not at all. It extracts these rich hidden features from the target model and feeds them directly to the drafter.
Okay, so let's walk through the inference steps. I type my prompt. What happens first?
First, the target model runs the prompt. That's the pre-fill stage. DFlash then extracts hidden representations from specific layers of that target model, and they sample these uniformly, from shallow all the way to deep.
So it's taking a cross-section of the big model's brain.
Right. Then it fuses these features together into something they call a target context feature. Here is the crucial differentiator from methods like EGLE.
Okay.
EGLE adds features to the input embeddings. DFlash does something much more powerful. It's called KV injection.
KV injection. Let's drill down on this. Why is injecting into the key value cache so much better? It seems like a very specific technical choice.
It is, and it's absolutely critical. If you just add context to the input, like a prefix, that information gets diluted as it flows through the layers of your draft model.
It gets weaker.
Yeah, it gets weaker. By the time you get to layer 5 or 6, that original signal is faint. But DFlash injects this target context directly into the key value pairs of every single layer of the draft model.
So every single layer of the drafter is being constantly reminded, hey, this is what the big model is thinking.
Precisely. It provides persistent, strong conditioning. It ensures that even if you make the draft model deeper, it stays tightly aligned with the target model's intent. It's like a guardrail at every step.
And then once it has that context, it generates the block.
Yep. It predicts the entire block of masked tokens in one shot using block diffusion. One forward pass, no loops.
Which brings us to training. Training a diffusion model for this sounds tricky. It's not your standard add noise, remove noise kind of thing you see with images.
No, it's quite specialized. The paper highlights 3 main innovations in training that really make this work. The first one is random sampling of masked blocks.
How does that differ from, say, standard masking like we see in BERT?
Well, usually you might just mask random words scattered through a sentence. But DFlash needs to simulate the actual inference process.
Right.
And in inference, you always have a clean token, the last verified one that acts as an anchor. So during training, they randomly pick these anchor tokens from the clean response and ask the model to predict the contiguous block that comes immediately after that anchor.
Oh, so it learns to complete the phrase starting from a known good point. That makes a ton of sense. It mimics the runtime environment.
It does. And the second innovation is loss weighting. This really appeals to the engineer in me because it acknowledges the brutal reality of speculative decoding. In this game, If you get the first token wrong, the next 15 tokens don't matter at all. They're just discarded.
Right. Verification stops at the first error. It's sudden death.
So treating all 16 tokens as equally important during training is just inefficient. Why optimize the 16th token if the first one is garbage?
Yeah, that's a waste of compute.
Exactly. So DFlash applies an exponentially decaying weight to the loss function. Token position 1 gets the highest weight, position 2 gets a little less, and so on.
It forces the model to prioritize the immediate future, like get the next word right or nothing else matters.
Exactly. It aligns the training objective with the actual utility of the model. It focuses the gradient on the tokens that have the highest chance of actually being accepted.
And what was the third point? Something about efficiency?
Shared embeddings. They freeze the target model's embeddings and the LM head, and the draft model just reuses them.
Ah, so it keeps the drafter really small.
Yeah, it keeps it functioning like a lightweight adapter rather than a completely separate brain. And that keeps the memory footprint low, which is vital when you're trying to squeeze this onto a GPU that's already loaded down with a 70B model.
Okay, let's talk numbers. We're here for the speed. Does this thing actually fly?
It flies.
Yeah.
Yeah, they benchmarked this on Qwen 3.8b and Alame 3.1. On the Math 500 dataset, which is a math reasoning benchmark, they achieved a 6.08x speed up.
6 times faster. That transforms a 10-second wait into a less than 2-second wait. That's massive.
It's a different user experience.
And usually when we see numbers like 6x, there's a catch. Like, oh, it's 6x, but the quality dropped by 10%.
Right, but here, because it's speculative decoding, the quality is mathematically identical. The target model verifies everything, so it's a free 6x speed up in terms of quality.
And how does it stack up against the competition, like Eagle 3?
Crucially, when they compared it to Eagle E3, which is the current heavyweight champion, DFlash is consistently about 2.5x faster.
Wow, that's a generation over generation leap.
It is. It's a huge jump.
And I want to touch on the reasoning models aspect again. The paper mentions thinking mode.
Yeah, this is a very relevant test given the current hype cycle. They enabled the thinking mode on Qwen 3, which generates those long reasoning traces. DFlash got about a 4.5x speed up there.
And since reasoning models are so verbose, I mean, they generate thousands of tokens just to think, that speed up is critical for the user experience.
It makes them actually usable in real-time applications.
Right. Now, a lot of papers show these great theoretical numbers that just fall apart when you put them in a real serving engine with high batch sizes. Did they test this in a production-like scenario?
They did. They integrated DFlash into Zhijian, which is a high-performance serving framework, and they tested it on NVIDIA H200 and B200 GPUs.
Yeah.
Even with high concurrency, a batch size of 32, they were still seeing speed-ups around 3x.
That's impressive. Usually speculative decoding just dies at high batch sizes because the GPU is already fully utilized.
Correct. The no free lunch theorem usually kicks in there. If your GPU is 100% busy just running the main model for 32 users, you don't have spare cycles for a draft model.
But because DFlash's drafting is O of 1.
And so lightweight, it drafts efficiently enough to still provide a gain even when the GPU is getting slammed.
Wait, I want to dig into the aha moments from the ablation studies. There has to be a trade-off somewhere.
Well, they looked at the draft model depth, and this is where the diffusion architecture really shines. They compared a 1-layer drafter versus a 3-layer versus a 5-layer.
And in an autoregressive world, going from 1 to 5 layers would make drafting 5 times slower.
At least. You're adding a ton of compute. But with DFlash, adding those layers added almost no latency because of the parallel execution. The matrix multiplication just absorbs it.
But the performance?
The acceptance rate, how often the draft was correct, went up significantly.
So you get a smarter model for free, essentially.
For almost free, yeah. The 5-layer model was the sweet spot. It was much smarter than Eagle E3 single layer, which led to longer accepted sequences.
So Eagle 3 is stuck with these shallow models because of that linear cost scaling we talked about.
Exactly. DFlash breaks that shackle. It allows us to have smart drafters.
There was also an interesting bit about block size generalization.
Yes, this is very cool. They trained a model with a block size of 16, but then they ran inference using a block size of 8.
And it worked?
It worked fine.
Why does that matter?
Flexibility. In a real serving environment, you might want dynamic scheduling. Maybe the GPU is slammed, and you only have the budget to draft 8 tokens.
Yeah.
Or maybe the prompt is really simple, and you want to try for 16.
You don't need to retrain the model for every single configuration?
Right. That's a huge operational advantage. It implies we could eventually have adaptive block sizes on the fly.
Which they said was future work, but the potential is there.
The potential is clearly there. It just makes the whole system more robust.
So, summarizing this paradigm shift, We've spent the last year trying to make small autoregressive models faster to speed up big autoregressive models. DFlash comes in and says, stop using autoregressive for drafting. It's the wrong tool for the job.
It really defines the lane for diffusion LLMs. We've been trying to make them the main brain, and honestly, they struggle with quality. But as a high-speed drafter, they are perfect. They provide the parallel structure that speculative decoding has been begging for.
It's like it's harnessing the target model's subconscious knowledge, those hidden states, and just using a diffusion adapter to project that into the future instantly.
That target context idea is the real game changer. It confirms that the big models effectively know the future tokens in their latent space. We just needed a mechanism fast enough to extract and decode that information without stepping on the brakes.
And DFlash is that mechanism.
DFlash is that mechanism.
For the ML engineers and researchers listening, the authors have released the code on GitHub, and the models are up on Hugging Face. The links are in the paper metadata, and I highly recommend diving into the Liang integration if you're running production workloads.
It's definitely worth a look. The implementation of the KV injection and the custom attention mask for the block diffusion it's very clever engineering.
That's a wrap on DFlash. It's rare to see a 6x speedup number that actually holds up to scrutiny, but this switch from serial to parallel drafting seems to justify it completely. Keep optimizing, and we'll catch you on the next paper.